The elastic behavior of solids can be explained by means of interatomic forces, the forces between atoms and their distances. This is a graph which explains it as potential energy U versus position vector R on the x-axis. You have to draw the graph like this, which explains that R naught is the distance between two atoms when the atom will be in stable equilibrium separation. When R is less than R naught, repulsive force is happening, and R is greater than R naught, attractive force is happening. The potential energy is negative when R is greater than R naught, and that's the graph you have to explain. And this can also be explained by means of spring ball model, where can you imagine the atoms to be small balls which are attached by means of a spring, and due to compression or extensions, you can imagine the spring getting contracted or extended and getting back to normal equilibrium. And so stress is just force by area, which is nothing but pressure. And different types of stress can be applied: a tensile stress, a compressional stress. A tensile stress is when the length of the body is extended. A compressional stress is when the length of the body is reduced, compressing it. Hydrostatic stress is when the force is applied on all directions. That's when the compressional stress, like you can imagine a gas exerting pressure on all the four sides of six sides of a cube. So on all sides, it's known as hydrostatic stress. A tangential stress is a body cube which is like this. Imagine it to be attached to the floor. If you're going to put a force or a pressure in this direction, tangential force, it tends to move like this and making an angle theta here. And this is known as, such a force is called tangential force, tangential stress. So strain is change in length by original length. Hooke did this experiment, Hooke's law, where he took a spring and attached a pan to it and added weight to the pan, and as the stress is increasing, there's a change in length by original length, which is known as strain. It's dimensionless because length by length is getting cancelled. What is the strain can be classified into longitudinal strain, volumetric strain, and shear strain. Volumetric strain is when the change in volume by original volume. A shear strain is, I told you, when you're going to apply a force like this, it's going to move, and the shear strain is this theta. What is tan theta is opposite by adjacent, where opposite is the relative displacement between the two parallel sides, by the L is the distance between two parallel sides. Hooke's law states that stress is proportional to strain. As stress increases, strain also increases, and stress by strain is a constant which is known as coefficient of elasticity. Coefficient of elasticity will also have the same dimensional formula as the stress, because strain is dimensionless. This graph between extension and load is a stress and extension is a strain, and it's linear. This was found by Hooke's. Then this graph is very, very important. It's a good 4-mark question which comes in every exam. It's a stress strain curve. Stress on the y-axis, strain on the x-axis. Okay, you should have to draw this graph like this, a straight line where it is between O and A, it's obeying Hooke's law. For a small amount of, for a large amount of stress, this small amount of strain. Large stress, small strain. Till OA, it obeys Hooke's law. Then till AB doesn't obey Hooke's law because it's not a straight line. But B is called elastic limit, where if you release the force or pressure, it gets back to, it traces back the same position, goes back to A, it gets back to its normal shape and size. But when B to C, what's happening? The C is called elastic limit. When you release the pressure at this point, it will not get back, not retrace its path, it will go in different path, thereby forming a permanent set. Like your rubber band will not come back to its original shape. I'm just talking about rubber band. It's not a rubber band, it's to do with the solids. Okay, elastic property of solids. Okay, so permanent set will happen. It will never get back to its original shape or size. It will be like a loose wire, and beyond which it's drastically increasing, and at D is the ultimate strength. Strength, or it's called tensile strength. Ultimate strength, beyond which you don't even have to increase the stress, or even on decreasing the stress also, the strain is going on increasing, and that is called fracture point. At E is called the fracture point when it will completely break. Between D and E, if you see, it will be non-uniform. I'm asking you to imagine a rubber band which consists of, it's not a rubber band, it's a metal. However, imagine a rubber band which has got neck and waist, and one part will be thick, one part will be so thin and all that. That's this DE part. when the area becomes non-uniform, and E is the breaking point in which it gets up, it breaks off. The plastic region is basically referred to as BE region. Starting from B, elastic limit, to the breaking point is referred to as plastic region. For a metal, the plastic region is quite large. Okay, and this is called elastic region, is from O to A. O to B itself can be categorized as elastic region because it's getting back to its original shape. This area inside this graph, the area in here, can you see this area? This area is called elastic hysteresis. Elastic hysteresis. That this area calculation will give you the amount of work done or energy lost. Energy will be lost in the form of heat or so then that's what it is. Let's go to next. This is a ductile material such as metal. You're talking about the plastic region, which is a large plastic region which exists here. Can you see? And this is a brittle substance where the plastic region itself is not there. This is a stress strain curve where, can you see, the plastic region is not even there. It immediately, the breaking point after B is just breaking point. B is the elastic limit. A is the proportionality limit. We are not talking about A here. We are talking about elastic limit, and the breaking point is a very small piece and so brittle it breaks. Ductile material. Okay. So what this is about, first one is ductile, second one is brittle, the third one is about malleable. Malleable metal, you're going to compress it. You're going to apply a force and compress it. The graph has to be like a third quadrant graph where this A dash is the elastic limit and B dash again is a point which is called crushing point or yield point, beyond which you can happily draw it into, on putting pressure, you can draw it into sheet. That's what it makes it malleable. Okay, malleable or malleability. Next, elastomers. This is what refers to as rubber band. Rubber band is an example of elastomers. All the other things that we're talking about can be steel or copper, buildings, everything in this world is elastic, though we don't see the elasticity much. The elastomers, the true example is rubber. Rubber, for a small amount of stress itself, this large amount of strain is parabolic. Can you see it's like a parabola? The graph itself is non-linear. The blood vessels are elastomers. And when the Young's modulus or modulus of elasticity is stress by strain, as strain is larger for a small amount of stress, Young's modulus is also minimum for a blood vessels and elastomers, rubber band. But let's talk about bulk modulus, a modulus of rigidity, in other words. It's change in volume by original volume when you're applying normal force, and so the K is the representation, and normal stress by volumetric strain. Normal stress is like pressure, by volumetric strain is delta V by V, which is here is reduction in volume, so I'm putting a negative sign. So 1 by K, reciprocal of bulk modulus, is also known as compressibility. The reciprocal of bulk modulus is often referred to as compressibility. Modulus of rigidity is related to shear modulus. Shear is this is becoming slanting like this, as I told you. That's a shear modulus, which is represented by eta, which is tangential stress by shear strain. Tangential stress is just force by area. Strain is tan theta. It's actually F by A by theta. The theta becomes a tan theta approximately, which is opposite, which is the relative displacement between two parallel sides to the distance between two parallel sides, and you get this. So let's go to next. Next thing is about elastic hysteresis. I told you for an I drew like this, where I had a permanent set here in the first one, which was for steel or copper or for any rigid material. For elastomers, it's going to come back to O, but you see that there's still an area for, this is when increasing the load, and this is while decreasing the load, the onward and the reverse, and it doesn't exactly retrace its own path, and so that this hysteresis loop indicates the loss of energy or work done per unit volume. Then generally we don't use rubbers in the wheel, we use synthetic rubbers in the wheel, because rubbers, as you know, due to heat, the hysteresis is large, hysteresis loop is large, so you have to choose a synthetic rubber which has got less hysteresis loop. Loss of heat due to loss of energy due to heat is less. And in the case of what is it, absorption. In the case of shock absorbers, we use vulcanized rubber. Vulcanized rubber, in the opposite, you have to have a big hysteresis, so that area will act as a shock absorber, where it will vibrate so much and transmit vibrational energy outside. So then, therefore, your jerk gets transferred into vibrational energy and goes out, and so you don't feel that much of a jerk. So, in the case of bike or car, thickness of a metallic rope. You all have seen a crane where a crane is lifting a container. That's called the load, and this is the rope, and the thickness of the rope can be decided based on the load that it's going to carry. You know, Shankar movie, they did this. The container was lifted by a crane, and they put so many people on the container and so many lights. The rope couldn't withstand and got cut off, and the accident took place. Many people died in Indian 2 set. So it's very important to determine what rope or what load, what should be the radius of the rope, what should be the load that can be attached. Normally, a crane and the rope are designed in such a way the rope can take 10 times more weight than it is capable of. So, for example, it's a container is 10 ton. The rope has been designed to carry. A container is 10 to the power 4 kg. Yeah. The rope is designed to carry 10 to the power 5 kg, so that there is a 10 times more cushion is there. Okay, so then they are talking about an ultimate stress here, which is force by area, where its mg is the load weight or container's weight by pi r square. So if you see, if you're taking your manufacture of a steel rod, you will say that this steel rod is capable of taking so much ultimate stress that will be printed there. So you know that m mass of the load, and you know the gravity, and a pi, I can just find r to be 3.2 centimeter, which is such a 3.2 centimeter. You can imagine 1 centimeter, 1 centimeter, 1 radius so big, 3.2, just the radius. It's like a rod. How can a rod be called a rope then? So that is the reason they make thin strands of rope, and they combine it so that the radius becomes 3.2, and thus it will flex it in order to increase the flexibility, and that's how it works. So next is about pillars. Why do we have to use I-shaped girders in the bridge? Or why should there should be a large depth and a small breadth? So this is a flyover. You would have seen an I-shaped girders on both sides, on which there will be a road, and you know that there will be length of the road and breadth of the road, and there will also be a depth of the road. And the question is, why should the depth be increased? By using an I-shaped girders, I am able to increase the depth. Why should it be increased? This formula is important. When a lorry goes on the road, it will create a depression, a yield, you know, and that depression is given by the weight of the load, that is lorry, the length L cube, by 4 into Young's modulus into breadth and to d cube. D is the depth. Depth is this is the depth, the original depth. That's getting cubed. So ideally, if you want less depression, you can make sure the depth is more, and if you make the depth more, it's also becoming cube. So all the more your depression will be less. Therefore let's not touch B. There's no need to touch B. Let's not touch B, because adjusting a D is good enough. No need to adjust a B. So that explains why the depth has to be more. Length has to be less. Obviously, the breadth can be more, but it's not desirable, because D is more is enough, because D is becoming a D cube. While moving traffic, the buckling of the road will occur. Moving traffic, moving mass is always greater than the static mass. A moving traffic can cause buckling of the road. So to prevent that, when the depth is more, buckling can occur. The depth is more, disadvantage is buckling can occur. So they artificially, to increase the depth, they're keeping the depth as it is, and they are putting a I-shaped girder, so that artificially they are increasing the depth. That is the reason the I-shaped girder is useful. So let's go to next. A hollow shaft is stronger than the solid shaft. The torque of a hollow shaft will be greater than the torque of a solid shaft. T1 is greater than T2. That's the proof. T1 is equal to again you should know the formula for torque. It's pi into shear stress, because turning stress is shear stress. This is a shear modulus, or what do you call modulus of rigidity, shear modulus. This formula you should mark up, and this is T2 and this is T1, and in this R will become this is a T1 will become, it's a hollow, so R to the power 4 will become R2 square minus R1, R2 to the power 4 minus R1 to the power 4 in the formula. And T2 will just be R to the power 4, and dividing T1 and T2, you get this formula. And actually before cancelling you should write volume, it's of the same material. Both the shafts should be made of same material, same volume. So equate the volume, you can replace R1 square minus R2 square as R square and get cancelled, and the numerator is greater than the denominator because R1 square plus R2 square is greater than R square, and that shows that the hollow shaft will require more torque than the solid shaft. And the Poisson's ratio last is about whenever you extend a wire, there is a change in length by original length. Along with that, there is also a change in the diameter by, when you increase the length, the diameter will decrease. This is called longitudinal stress. This is called lateral stress, change in diameter by original diameter. A lateral stress by longitudinal stress is what is called sigma, which is nothing but Poisson's ratio. That's all. This is what I took. You have to do the numerical on your own